There we go. Okay. Wonderful. So, so that's what I was going to say about that. So if you're doing your 1.1 WebAssign homework and you're wondering why it keeps marking you wrong on these numerical table values, just make sure you hover over the decimal that you're actually looking at. So whatever that Y value is, look at the bottom one, that's the full decimal. The one up here is just rounded so that they can fit it into the box. Because, you know, if you round this down to however 3 decimal places or however many will fit in this box, you end up just rounding this off to negative 0.1, which is why the answer is listed as such. So refer to this value here at the bottom. Any other questions from the homework? I got a bunch of them today through WebAssign, but most of them were related to this issue. So it seems like this homework for most of you went a lot more smoothly than the pre-calc review, which I guess makes sense because the topics for this homework were much more specialized, I should say. Yes, I'm looking at your scores here. I mean, the homework for 1.1 isn't due until tomorrow, but it looks like most of you, more than half of you at least, got all of it done. So that's good. Yeah, I know. And with these summer classes, it's like you have to stay on top of it. Okay. Well, if you don't have any homework questions, let's just get to it. I want to remind you that you do have some asynchronous work that you're going to have to do over the weekend. So tonight I'm going to go over 1.2, maybe a little bit of 1.3. We'll kind of see how far we get. 1.2 for sure. But there are just a lot of rules in 1.2, and it's kind of, sorry, I don't want to say it's kind of a drag, but it can be kind of a drag just because you're going through lots of theorems and it can be a little boring sometimes. Sorry, I can't help it. Just, that's the way it is. And then wherever we stop at 8:10 tonight, I'm going to pick that up after class at some point for your asynchronous work. And if you're not familiar with all the lingo for e-learning, asynchronous just means like you're doing it on your own time. You're going to watch a recorded lecture. If you were not here the first day of class, we cannot fit Calc 1 into 3 nights. It's not normally scheduled on 3 nights. It's normally scheduled on 4, but you guys have an asynchronous night. The other Calc 2 classes, half asynchronous, half live. So you guys have a little bit more live time. My husband was like, just do 2 days and then make them do the other 2 offline. But I really like to have you live. I think it's, I just really think it's better. Everybody seems to like it better. Okay, so for your, I'm going to send you an email, by the way, as soon as I record your asynchronous lecture. And anything from that will be due Monday. And then anything that I teach tonight, the homework will also be due Monday. So anything from tonight and then anything that you have to do over the weekend for asynchronous is Monday. So whatever you learn tonight, obviously you're going to learn right now. I'm going to record the asynchronous lecture tonight at some point, and then you will have the option of doing it super early in the morning tomorrow, or you can, if you want, do it Monday afternoon. I wouldn't recommend that because you're going to have a quiz that will also include questions from your asynchronous work on Monday, because your quizzes are Mondays and Thursdays. But we'll see. I don't know exactly how I'm going to do this yet, but I'm definitely going to record it tonight just because I want it to be available to you as soon as possible. I'm going to get off of this call at 8:10, and I'm going to go hang out with my kids, and then I put them to bed at like 9 something. And then I go work out on my Peloton. So I'm not exactly sure if I'm going to do the recorded lecture before that or after that. So it should be interesting. I don't know. We'll see. All right, 1.2 though, right now. Does anyone have a question about that whole concept that I was just discussing with the asynchronous lecture? Okay, but it'll be up to you. And part of the reason I want to make sure we have less asynchronous time in our class versus like half asynchronous is just because I know how challenging it can be to force yourself to do something when it's not actually like scheduled into your time. So you're going to have to make time to do that. I think you guys will be good though. Good feeling about it. Everyone's been pretty on top of the homework. All right, 1.2. Limits of functions using properties of limits. I have to go hook up a fan because it is just like insanely hot over here by this window. 1 second. I deal with papers flying everywhere. Hopefully, I can limit that. Okay. I'm going to be giving you guys a bunch of theorems, like I said, about how to find limits using properties of limits. And then we're sort of going to put all of that together to really talk about how to find limits algebraically. So we're not going to be using tables today. We're not going to be using graphs quite as much. You might see a graph here or there. Mostly we're just going to be focusing on how to find these limits using these properties, and then we're going to put them all together. So I'm going to sort of lay them out piece by piece for you. The first one is the limit of a constant. If f of x equals a, where a is a constant, then for any real number c, the limit of f of x as x approaches c is equal to the limit as x approaches c of a, it's f of x equals a. And this limit is just a. Now, this is a theorem. This means that there's something that someone somewhere along the line has proven using some sort of axiom, and you're being given the conclusion from that proof. So this is just some stated truth that you can use throughout this class. The limit of a constant, well, if that constant is a, the limit of a, no matter what value x is approaching, is going to be a. And I'm going to show you why. If you can imagine some constant function a, remember if f of x equals a and a is a constant, that's like saying y equals a constant. And a y equals is a horizontal line. We graphed one of those the other day for those of you who haven't had math in a while. I don't know what it is, but let's say maybe it's right here. Let's say that y equals a or f of x equals a. Now, it could be sitting anywhere. It could be up above the x-axis. It could be below the x-axis. Does not matter. We can pick any value c that we would like. And what you're looking at here is the value that y is approaching as x approaches c from either direction. So as x approaches c, you can see that all the time, y is going to be at a all the time. So it doesn't matter if we're approaching from the left or from the right, y is always going to be approaching a because y is a all the time. So the limit of a constant is the constant itself. Sometimes I just write that in English words because it's something that we're going to use more often than you might imagine. The limit of a constant is the constant itself. Questions on that one? Excellent. So I'm just going to give you a little example to go along with each one of these. There's not a whole lot to do for something like this, but just one example that illustrates this theorem might be the limit as x approaches -2 of 3. Now 3 is a constant function. It's just the horizontal line that goes through the y-axis at 3. Its limit is always going to be 3 no matter what. So it does not matter what value x is approaching. I mean, we could have put c here, 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 here. It doesn't matter. The y value is always going to be 3 in this instance. Okay. The next theorem is the limit of the identity function. The limit of the identity function. If you don't remember the identity function, it's y equals x. It's kind of just that mirroring effect. Whatever value x takes on, y takes on. If you want to see this graphically, we looked at an identity function the other day. It's just that 45-degree diagonal. Y equals x. Sorry. I've been bugging my husband to get a ceiling fan put into this room, but now we can't even get the electrician over because it's too hot in the roof, and he's not going to work on it like this. Therefore, I have this fan just like pointing at me, blowing things everywhere. He didn't want a ceiling fan. Maybe he was strategically waiting until it got too hot to get the electrician over here. If f of x equals x, then for any real number c, the limit as x approaches c of f of x is the limit as x approaches c of x, and that is going to be c. Now, you can see why if you look at this graphically, because this is the identity function, and imagine you have some value c, doesn't matter where you put it. Let's say we put it right here. As x approaches c from the left or the right, the y value is going to be approaching whatever y value this value is. But this value on the x-axis is going to be the same as the corresponding value on the y-axis because it's the identity function. So whatever the x value is, the y value is also that same value. So if you're looking at the function y equals x, as x approaches c, the limit is going to also be c. There's that. And then just a little example that goes with this might be the limit as x approaches -2 of x. Now, as long as your function is just x, you can just say that whatever value x is approaching, the limit of that function has to take on that value. Questions there or so far? Okay. The next theorem is for the limit of a sum or difference. If f and g are functions for which the limits both exist, so the limit as x approaches c of f of x, and the limit as x approaches c of g of x both exist, then the limit as x approaches c of f of x plus or minus g of x is just going to be equal to the sum or difference of their limits. So we can take either the limit of the sum or difference, or we can take the sum or difference of the limits. It's a little bit harder to do online because in class I can see if everyone's still writing my theorems and if they need more time, but I can't really tell right now if you guys are still writing or not. So if I'm going too fast, you'll have to let me know. All right, so an example of this would be maybe the limit as x approaches -2 of the function 3 plus x. Now, some of you have had calculus before, and you might be like, okay, what the heck? Why is she breaking this down so far? We are going to pull all this together in the end, but I'm kind of showing you right now how the properties work together. This is just the sum of two functions. One of them is a constant function, and the other one is the identity function. To find the limit of this sum, we can take the limit as x approaches -2 of 3 and add that to the limit as x approaches -2 of x. So instead of taking the limit of the sum, I can take the sum of the limits. And now these limits we actually already found in the preceding two examples, but the limit of a constant is always the constant itself. And the limit of the identity function is just whatever value x is approaching. And you're just summing these up. So 3 plus -2 is 3 minus 2, which is 1. Okay, heard a beep. Okay, Morgan, what's your question?
How did you know if it was a plus? Like in 3 plus -2. Like, how did you know that was a plus sign instead of a minus sign?
Oh, just because I already had the plus built into the function. So when I split it up, I kept the plus. And then this limit was -2. So I just had the plus that just kind of stayed from here to here to here. I'm going to show you one with the difference too, though.
Okay, that makes more sense.
Yeah, but it just carries its way through. But if you want to contrast that with a difference, another example of that would be the limit as x approaches -2 of 3 minus x. And you could do the same thing. You could say the limit as x approaches -2 of 3, and then just carry that minus sign over. And instead of taking the limit of the difference, take the difference of the limits. So when you apply the minus sign, that sign stays, and then you just leave the x alone. You don't say it's -x. I mean, I guess technically, well, we don't really have a theorem for that yet, so do that anyway. The limit of a constant is the constant itself. The limit of your identity function is whatever value x is approaching. 3 plus 2 is 5. What I need is a fan over there that like blows at me this way. What's always something. All right, questions on the sum or difference? Wonderful. Let's talk then about the limit of a product. Remember, a product is the answer that you get when you multiply quantities. If f and g are functions, for which their limits both exist, then the limit of the product exists. Of x times g of x. And this is equal to the product of the limits. Just use brackets. So what this is saying is that you can take the limit of the product of your functions, or you could break it up and take the product of their limits individually. There's a corollary for this, and it has to do with a constant multiple. So I'll give you that. A corollary is kind of just like something that comes out of a proof, just not really like a part two, but it's sort of like a result of your theorem. If g is a function and the limit of g of x exists, and if k is a real number, then the limit as x approaches c of k times g of x exists, and it is equal to k times the limit as x approaches c of g of x. So I'm going to give you two examples. One of them is going to use this constant multiple rule, and the other is going to use the limit for the product of two functions. So the difference between the two is that for the limit of a product, f and g are both functions of x, meaning like there's some sort of expression having to deal with x inside the function. So it could be any number of things. I'll give you an example. The corollary is just for if your other function is a constant. So just some number multiplied by another function of x. So this is a little bit more of a basic variation of the limit of a product. What this is saying is that instead of multiplying your constant multiple inside your limit, you could pull that constant multiple out and take the limit and multiply it by that value. So what this would look like in an example would be something like the limit as x approaches -2 of 3 times x. Now I'm trying to give you this same example over and over again, just in different scenarios. But 3 is your constant multiple in this case. X is your function of x. So we can rewrite this as 3 times the limit as x approaches -2 of x. Now this one we've found a bunch of times already today. The limit of the identity function is just whatever value x is approaching. So we're just going to multiply that by 3. So you'd have 3 times -2, which is -6. Now, you don't have to pull that out. Later on, you'll synthesize all of this together. But it's something that you could use, and you probably will use it. You definitely will use it when we start talking about limits and infinity next week. And then, for the product of functions, maybe consider something like x squared. I haven't given you a theorem for how to deal with a polynomial function yet. I will in a few minutes. But for right now, we can use the limit of a product. And the way we would do that is by breaking up x squared into x times x. And now you have the limit of a product of two functions of x. And that means that you could change the limit of a product to the product of the limits. Like that. And then again, we're using this same concept that with the identity function, the limit is whatever value x is approaching. So we would say that this is -2 times -2, a negative times a negative is a positive. You get 4. And I know some of you have had calc before and you're like, why are we doing it this way? You don't have to do it this way all the time. I'm illustrating to you how to use these properties. It's really important that you understand what properties are available to you so that you know what you can and cannot do with limits. All right, questions so far? We're going to do a piecewise function next. Okay. Actually, I want to give you the rest of these theorems first because I'd rather do that before I give you the piecewise function. Yeah. We'll hold off on it. Okay, so leading off of this, we have the corollary for the limit of a power. If the limit as x approaches c of f of x exists, and if n is a positive integer, my calc students seem to never know what integers are. You know what they are, you just don't remember what they are called. Remember, integers are whole numbers that can also be negative. Whole numbers start at 0 and they're 1, 2, 3, 4, 5, 6, so on and so forth. Integers also can take on negative values, but we're not talking about like, you know, negative a half. That would not be an integer. -1 would be an integer. Okay. If that is the case, then the limit as x approaches c of f of x to the nth power is equal to, and this one's actually kind of cool. Students always forget about it, and you'd be surprised when it actually starts to come in handy. Sometimes not even until Calc 2. The limit of f of x to the nth power. So this is saying that instead of taking the limit of your function to the nth, you could take the limit of the function and then just take that whole limit to the nth power. Now, technically, I could redo this example using the limit of a power, but I'll give you another one just so that you can see how it works a little bit differently. Change it up a little bit. So this would be for something like the limit as x approaches -2 of maybe x to the 4th. Instead of actually trying to multiply that out 4 times using our previous theorem, you could just take the limit as x approaches -2 of x and take the whole limit to the 4th power. You savvier students will remember this, and in Calc 2, you're going to apply it when you least expect it, when everyone else has forgotten about it. It will come up again. So now I can take this limit, which is just that limit of the identity function, which we've done a bunch of times, to the 4th power. And -2 to the 4th power, well, negative anything to the 4th power is going to give you a positive value, and then 2 to the 4th is 16. Similarly, we have the limit of a root. I told you it's a lot of theorems today. Sorry. If the limit as x approaches c of f of x exists, and if n greater than or equal to 2 is an integer, then the limit as x approaches c of the nth root of f of x. This is another good one that we'll come back to later. Can also be rewritten as the nth root of the limit as x approaches c of f of x, meaning that you could take the root of the function and then apply the limit, or you could apply the limit and then take the nth root of the limit. Note that n has to be greater than or equal to 2, and it has to be an integer. So you're talking about square roots, cube roots, fourth roots, fifth roots, so on and so forth. This is provided that n is even. Oh, so sorry, I shouldn't have said third roots, fifth roots. I was going a little crazy with my integer conversation. Provided your function is positive if n is even. So that's a little caveat for n being even. We can't take the even root of a negative function. But I mean, assuming that you have n being even, that's an issue. But you can take the nth root for an odd n regardless. And then I will pop this little example down here just because I don't want to have to start a new page just for this little example. So this would be the limit as x approaches -2 of the cube root of 4x. So you can rewrite this as the cube root of the limit as x approaches -2 of 4x. And then you can even use the constant multiple to take that constant multiple out of your limit, which I just forgot to do. Hold on. I'm carried away here with my limits. So I can rewrite this by taking that constant multiple out and writing it as 4 times the limit as x approaches -2 of x. And this will be the cube root of 4 times. And then here we have that identity function again, -2. Little multiplication dot in there. So this is the cube root of -8. And remember, we can take an odd root of a negative number. We just can't take an even root of a negative number. So your limit here is -2. Questions? We have a theorem for the limit of a fractional power. And this would be f of x to the m over nth power, some sort of rational power. If the limit as x approaches c of f of x exists, and if f of x to the m over nth power is defined for positive integers m and n, You could probably figure out where this is going based on everything we've done so far. But the limit as x approaches c of f of x to the m over nth power means that you can take that entire limit to your fractional power. The example that would go along with this might be something like the limit as x approaches 4 of x to the 3/2. You could rewrite this as the limit as x approaches 4 of x, and then take the entire limit to the 3/2 power. Now, it's an identity function, so I know that for the identity function, the limit is just whatever value x is approaching. So my limit value is 4. You can take 4 to the 3/2 power. If you're not used to doing this, you could always do it in your calculator, but remember that 4 to the 3/2 is really 4 to the 1 plus 1/2. And we're going to be using the 3/2 power a lot, and I would hate for you to feel like you always have to use your calculator. As long as I'm adding the exponents, I can actually split this up into 4 to the 1st times 4 to the 1/2. So that's from your properties of exponents. The property looked something like, how did you see it back in the day? Something like this. It's a product rule for exponents. You can take the, if you have the same base and you're multiplying, you add the exponents. Same idea here. I've just broken it up in the opposite direction. And then we know that 4 to the 1st is 4. 4 to the 1/2 is the square root of 4, which is 4 times 2, which is 8. So yes, you could technically enter 4 to the 3/2 in your calculator, but I hope you'll start to get really comfortable with these 3/2 powers, especially for something like 4, where you can actually get a number to pop out of there. Questions on that? So here's a theorem I've been waiting for. The limit of a polynomial function. I thought we would never get here. This is a biggie. If p is a polynomial function, if you don't remember what a polynomial function is, we did talk about it on the first night, but it's basically a collection of constant multiples and variables to powers that are positive integers. And it's just a collection of those terms. So, you know, like 3x to the 5th minus 2x to the 4th plus 3x squared, so on and so forth. Polynomials don't have any radicals in them, I should say polynomials don't have variables under radicals. They also don't have any variables that are being taken to any fractional exponents. They don't have variables in the denominator or any sort of variable that's going to a negative exponent. So if p is a polynomial function, then the limit as x approaches c of p of x is p of c for any c. So that basically means that you can just evaluate your polynomial at C. And that's it. So of course I will give you examples on that. We're going to evaluate the following limits. We'll take the limit as x approaches -1 of 3x to the 4th minus 2x cubed plus 4x. This is a cube. I'm going to rewrite my 3 so it looks more 3-ish. And this is a polynomial function. So I can go ahead and just evaluate this for x equals -1. So we're going to write this as 3 times -1 to the 4th minus 2 times -1 cubed plus 4 times -1. And you guys evaluated a bunch of functions on your pre-calc WebAssign homework. If you want to plug that into your calculator, be my guest. You really shouldn't need to. -1 to the 4th is +1. -1 cubed is -1. What was I going to say just now? Remember your order of operations. Before you can multiply, you must apply the exponent. So don't take 3 times -1 and take that to the 4th. Don't do that. You must take -1 to the 4th before you multiply by 3. So if it's been a while since you've done this, you got to remember your order of operations. Please excuse my dear Aunt Sally. 3 plus 2 minus 4 is 1. Now, of course, we could have found this limit by breaking this up and saying it's 3 times the limit of x to the 4th power minus 2 times the limit of x to the 3rd power, but you don't have to. So you know the properties, you know what you can and can't do with the limits, but if you can just evaluate it, do that. And that's what I was thinking earlier with every time I have students who've had calc before, they're like, why are we doing all this when all we really need to do is just plug it in? You technically need to know the properties. The limit as x approaches 2 from the left of x plus 1 times 3x squared minus 9. Now, I think I added this example and said from the left because I think the book had one like this in there, and that was my rationale. I didn't want you to see it on your WebAssign homework and be like, whoa, wait a second, she didn't show us one like this in class. But it's a polynomial. Polynomials are continuous throughout their entire domain. Therefore, whether you approach from the left or from the right doesn't make any difference. You're still going to be looking at the same value for the limit. So if you're, I just didn't want you to see it on your homework and be like, oh my gosh, like the sky is falling. It does not matter for a polynomial if you're approaching from the left or from the right. You're still going to get the same limit value. It's a polynomial function. Go ahead and just evaluate it directly. Now, if you want, and I think the easiest thing to do here would just be to take these limits separately. And just multiply what you get here for these products. So the limit of a product is the product of the limits. And then you can take each one individually and multiply their results together. If I were you, I would not go through and FOIL this. Don't do more work than you have to. So for this one, you're going to get 2 plus 1. And then for the next one, you'll get 3 times 2 squared minus 9. So this leaves you with 3 times, don't multiply 3 and 2. You first must take 2 to the 2nd power. 2 squared is 4, times 3 is 12, minus 9 is 3. Questions here? Let's do one more. This is the limit as x approaches 3/2. The function is 4x squared plus 8x minus 5 to the 3/2 power. Okay. Yes, technically you can just evaluate this directly. Officially, I didn't really give you a theorem for that. It's not the end of the world though. Just go ahead and take the limit of the inside function and then take your entire limit to the 3/2 power. So this is that limit of a fractional power theorem. So we are going to take 4 times 3/2 quantity squared plus 8 times 3/2 minus 5. And that whole thing is getting taken to the 3/2 power. So the inside is a polynomial, so we're just using that polynomial rule here. So you're getting 9 plus 7 to the 3/2. And this gives you 16 to the 3/2. When you see the 3/2 power, remember you can always split this up into 1 and 1/2. So the value times the square root of the value. And look at that, you don't use your calculator at all. Renee, yes. Every time it beeps, there's like a delay until I see what actually happened. Tell me, Renee, what's your question?
Isn't it 16 3.5? So shouldn't it be 16 with a cube root or a cube power?
Yeah, so I used this same rule again that we used up here. So whenever I see a 3/2 power, I split it up into 1 plus a half.
Oh, I'm okay.
Yeah.
I see.
No, it's fine. It's fine. I just do this all the time because I just feel like it's easier, because I hate having to plug these into my calculator because I always feel like, oh, that was such a waste of battery power. Like,
yeah,
waste of effort. So I take my 3/2 and I split it up into 1 and a half.
Okay, thank you.
You're welcome. Yeah, I'm glad you asked. Other questions on any of these examples A, B, and C? Okay. So the last theorem I have for you is the limit of a quotient. I know everyone's just like, oh, thank goodness. And then I'll give you some more examples where you're going to have to use some other algebraic techniques. So theorem, limit of a quotient. If f and g are functions, for which the limit as x approaches c of f of x and the limit as x approaches c of g of x both exist, then the limit of their quotient exists. The limit of f over g is equal to the limit of f divided by the limit of g. Now this is provided that the limit as x approaches c of g of x does not equal 0. Because we cannot divide by 0. I'll give you an example of that. Then I'll give you your piecewise example I got to go back to. And then we'll talk about some indeterminate forms. So an example of something like this would be the limit as x approaches 4 of 3x minus 14 divided by x plus 1. Whoops, sorry. Screw this up. So we can go ahead and, if you want, actually write out the split, but you don't actually have to write out this limit divided by that limit. I mean, you're going to be doing so many of these, it's not a big deal, but officially you're taking the limits of the different, you're taking the limit of the quotient of these two polynomial functions. So 3 times 4 minus 14 divided by 4 plus 1. You get negative 2/5. Now, I really want you guys to be able to sort of think in between these different methods that we have for finding limits. Of course, you can always go to your graphing calculator and look at your table or look at this function graphically and verify this limit. So if you ever weren't sure about your algebra, you can always put this into your y equals and then look at what happens to the values of the function as you approach 4. And just verify that you end up approaching negative 0.4, negative 2/5, whatever your calculator gives you. So this is not like some major departure from what we did yesterday. It's the same thing, just using a different method. Okay, your daily piecewise function. I feel like we should do one every day, all semester. I made my algebra students do like a factoring problem where the lead coefficient was not equal to 1, like every single day of the semester, just because just seemed like they never, or like maybe my calc students could never do it. I don't know. I just was like, you people need to do this every day. I'm sure it was very beneficial. All right, so this will be a 2-definition piecewise function. For f of x equals 2x minus 1. Now this will be for x greater than or equal to negative 1. And negative x minus 1 for x less than negative 1. I'm going to ask you for 2 different limits. The first one will be find the limit as x approaches 0. Of f of x. And I'll give you the second one in a minute. Well, let's go ahead and graph this. So our boundary is at -1. So that's where the interesting stuff happens. So notice I'm not actually asking you for part A to find the limit as x approaches -1. So this limit should be very boring once we get this graphed. But for the positive values, or I'm sorry, for the values to the right, for x being greater than or equal to -1, I'm looking at 2x minus 1. And since we're greater than or equal to -1, I know that we're going to be sitting here on the y-axis at some point. So I'm just going to go ahead and use y equals mx plus b. The y-intercept is -1. And the slope is 2. So I know I can go up to right 1, up to right 1, so on and so forth. Now, right now, I'm only doing this for values of x that are greater than or equal to 0. So I am going to have to include another piece of this that takes me down towards x equals -1. So if I go, instead of up to right 1, if I go down to left 1, I'll get over here. And because x equals -1 is a part of this definition of the function, I can fill in the circle. Sorry, now it looks like it's not connected. Here we go. So this point is at -1, -3. Your y-intercept is at 0, -1. Our other function is -x minus 1. If you want, you can apply the same logic. The only difference is that we can't actually use the y-intercept in this case. You can plug in a table of values if you'd like. Maybe I'll just do that for ease of use, I was going to say. -x minus 1. Okay, remember that for the piece where our boundary is not defined, so I don't have the equal to symbol on x is less than -1, it's just strictly less than, I still want to evaluate it at that boundary point, but remember, we're going to leave the circle open there. So when x is equal to -1, I'll have -1 minus 1. So I should have moved my table over a little bit. -1 minus 1 is actually 1 minus 1, which is 0. And then we'll keep going left. When x equals -2, I'll have -2 minus 1, which is 2 minus 1, which is 1. And now you can kind of see where this is going, especially if you consider the slope being -1. But if you want to do one more, go ahead. -3 minus 1 is 3 minus 1, which is 2. So as x goes left each unit, your y value is going up 1. So we're going to put an open circle at -1, 0. And then we'll have a closed circle at -2, 1. And a closed circle at -3, 2. And your slope is -1, so you know it's always going down 1 and over 1, and it must be heading down from left to right. There's your piecewise function. Does anyone have a question about the piecewise functions graph? I hope we're feeling more comfortable with these. All right, let's look at the, actually we have two ways of doing this. I kind of wanted to just graph it because I think that we need practice doing that. I think for right now, we should find the limit in two ways. We should use the properties that we've already talked about today, and then we should verify that by looking at the graph. So what we learned today was that for polynomial functions, we can evaluate the limit by using direct substitution. So in order to find the limit as x approaches 0, we're going to use the definition of the function that corresponds to the value 0. So 0 is not less than -1. So I'm not going to use the function -x minus 1. But 0 is greater than or equal to -1. So I know I'm going to use the first definition of the function when I evaluate this limit. So I'm going to use the 2x minus 1 piece of the function. And it's a polynomial, so I'm going to go ahead and evaluate it directly. And get a value for the limit of -1. So if I did not specify that how I wanted you to find the limit, you could always use this method of direct substitution. I do, though, want to verify this graphically and kind of tie this in with what we did last time. Look at what's happening to your graph as x approaches 0. So we're not approaching 0 on this left wing. I mean, not really. I mean, we don't really get very close. It's on the right wing of the graph on which we're approaching 0. So as x is getting smaller and smaller and smaller, your y value is getting to be smaller and smaller and smaller. And as x approaches 0 on the right, you end up approaching a y value of -1. Well, that's what you just found here. Now, note that you can approach this value of x equals 0 from the other direction as well. So if I were to approach 0 from the left, I'm starting at values of x that are smaller than 0. And as I approach from the left and head towards the right, my x value will continue to increase towards 0, and the y value will continue to increase towards -1. So you can see how graphically this matches up with the limit that you found here for part A. Are there any questions about part A? So you might guess then, for part B, I'm going to ask you to find the limit as x approaches -1 of f of x. We got to make this a little more complicated. All right, so again, we have two ways of doing this. I think for approaching this boundary, honestly, looking at the graph is probably the easier way of doing it, but we also need to know how to do this analytically because we're going to be doing more stuff like this analytically. So what we're going to do here is, since -1 is our boundary, we're going to approach -1 from the left and from the right. So I'm going to first talk about, let's approach x, or x equals -1 from the left. Now, when we do that, when we approach -1 from the left, we're approaching -1 from values that are less than -1. When we do that, we're on this function, -x minus 1. And I'm going to get the limit value by using direct substitution. So I'm going to take -1. I kind of don't like this second set of parentheses, so I'm going to do this. -1 minus 1. And we know that 1 minus 1 is 0. Do something similar, but now approach -1 from the right. When you approach -1 from the right, you're approaching from values that are greater than -1. When we're greater than -1, we're following the first function definition. So you'll have twice -1, -1, -2, minus 1 is negative 3. The big takeaway from this is that when we took the limit as we approach negative 1 from the left, we got a different value than when we approach negative 1 from the right. And you know that if your left and right limits don't agree, then the limit of the function does not exist at whatever point you're looking at. So we would have to say that the limit as x approaches negative 1 of f of x does not exist because the left and the right limits do not agree. Now, like I said, this one, most of the time it's easier to use direct substitution. For something like this, I think as long as you have the graph is a little bit easier to see things with. But as you're looking at the value of x equals negative 1, you're seeing this huge gap in the graph. Now, we're going to be talking more about that when we discuss continuity. But in this case, you can clearly see that as you approach negative 1 from the left, the value of your limit is not the same as when you approach negative 1 from the right. And because the limits are not the same, the limit of the function does not exist at that point. I feel like that one conceptually is a little bit trickier. Does anyone have a question there? Then let's talk about some situations where we have some indeterminate forms. Oh. I'll just call this more examples. This section in your book is kind of weird because it goes from talking about properties of limits to then going through these examples, which are usually in a whole section of their own because they're very, very important. So when I say more examples, I don't want you to think like, okay, we're just doing more of the same thing. These are some really important examples that have a little bit more of complexity as far as algebra is concerned. And I don't want you to think that they're just being stuffed into the end because they're not very important, because these concepts are very important. You're going to see a bunch of these. If you took Calc 1 in high school, you learned to use something called L'Hopital's rule. We don't teach that at ECC in Calc 1. I don't know why, because it's actually in our book in chapter 4, I think. But we're going to have to do these algebraically, and you'll learn to use L'Hopital's rule in Calc 2. So if you try to use L'Hopital's rule in this class, you will not get credit for your limits because I want you to find these limits algebraically. So an example would be something like this. The limit as x approaches negative 2 of x squared minus 4 divided by x plus 2. I think I'm done with this stand now. I just don't know. The funny thing is I'm always returning fans because they're not loud enough because we sleep with the fans on. Now I'm wishing I had a quieter fan because I'm trying to teach and I have a fan that is only loud all the time. I want you to try to do this with direct substitution, and I want to see I want to show you what happens here. If we go ahead and just focus on evaluating the polynomials in the numerator and the denominator separately, you'll get -2 squared minus 4 divided by -2 plus 2. Well, don't forget that -2 squared, I talked about this last time, but it's so important that I'm going to talk about it again. -2 squared, oh, it's right there actually. I don't even have to redo it. -2 squared is 4. -2 squared is -4. So make sure that you're using parentheses when you need them. This means that you're taking the value -2 and multiplying it by itself. This variation without the parentheses means that you're taking 2, squaring it, and then taking a negative of that value. It's a very, very common mistake. I want to make sure that you don't have that problem. Someone mentioned to me also today, since I'm on my calculator, that they kept getting errors when they were entering negative numbers. Make sure that when you're entering a negative number, you're using the actual negative sign and not the minus sign. I know some of us have a lot more experience with calculators than others. During a normal semester, they offer a graphing calculator workshop, but in the summer, I guess they don't have it. So there's that. Okay, so -2 times -2 is +4. And you end up getting this quantity 0 over 0. I really want to note to you here that 0 over 0 is not 0, and it's not undefined. A 0 over 0 is an indeterminate form. That means that you can't make a conclusion regarding the actual value. So you have to do a little bit more work here in order to find the value for the limit. I can talk about this till I'm blue in the face, and there will still be 1 or 2 students who will get this value of 0 over 0 and then tell me either it equals 0 or it's undefined. They'll say, oh, the limit does not exist, or they'll say the limit is 0. This is not a DNE situation. It could potentially be one, but we need more information. That's sort of what the indeterminate means, is like we can't really make a conclusion yet. So what you have to do in situations like this is you have to rewrite the function such that you don't get an indeterminate form. Now, for something like this, you might be noticing that if you factored the numerator, you would actually have a difference of 2 squares, and you could cancel out this factor in the denominator. Yet that is completely fair game for limits. You can rewrite your expression with an equivalent expression, and the limit will not change. So I can rewrite this as x plus 2 times x minus 2 using the difference of 2 squares. And then I can cancel out these factors of x minus 2. Now remember, I have to be able to factor it before I can cancel it, and that's what I did. And what that leads you to then is the limit as x approaches -2 of just the quantity x minus 2. Now, when I talk about continuity in the next section, I'm going to talk about what type of discontinuity we have and how it's removable and how that looks on your graph. Right now, I just want you to look at these limits analytically and figure out algebraically how to work around these indeterminate forms. I can go ahead now and evaluate this limit at -2, and I'm going to substitute -2 for x. We'll get -2 minus 2, and you'll get a value of -4. That's how you would do something like that algebraically. Now, you probably had a very similar question to this on your 1-1 homework, but you worked on something like this using a table. And if I gave you something like this on your 1-1 homework in WebAssign, it didn't matter that the function value didn't exist at -2 because you were just looking at the values as you approach -2 from the left and from the right, and you would have made a conclusion that the limit was -4. This is just doing the same exact thing in a different way, just using some algebraic techniques. And honestly, that's what my calc students are usually more comfortable with anyway. All these tables and stuff, they're like, what is this weird thing we're doing? And as soon as I start factoring and canceling, everyone feels a little more comfortable. So this is an algebraic technique. I'm going to specify on your exam if I want something done using a table, if I want something done using, if I want something done graphically, I'm probably just going to give you a graph and say, look at this graph and tell me about the limits, kind of like I did on your quiz today. If I want it done algebraically, I'm going to state that. So if I ask you to do something like this on your test and I say you use some sort of analytical approach or some sort of algebraic approach, this is what I want to see, not a table. I made a mistake in the past of saying that students could use any method, and I just assumed that they would do this algebraically, and then they used a bunch of tables, and I was like, ugh, really, that's not what I was trying to test them on. So I've had to be very specific about what I want, just because I want to make sure that, I mean, I had to give them the credit in that case because I didn't specify, but if I want to see something specific, I kind of have to give you a little more guidance. So you'll know on your test what method I want to see. Questions on A? Okay. B. This is the limit as x approaches 1. And this is going to be the difference of two rational functions. 1 over 1 minus x minus 2 over 1 minus x squared. And this one is going to take you back to your algebra days. Okay, so go ahead and use direct substitution here. You'll get 1 divided by 1 minus 1. Oh, already we've got some problems. You get 1 divided by 0 minus 2 divided by 0. This is actually an indeterminate form. And for those of you who are thinking, wait, why is it indeterminate? Why isn't it just like the limit does not exist because we're dividing by 0? Well, technically, when you're dividing by 0, you're getting some sort of infinite quantity. I want to show you why, actually, because I think it'll be helpful to see this on your graph. I'm going to look at these two functions. The first one is 1 over 1 minus x. Technically, we're not talking about infinite limits until Monday. But I kind of want to show you what's happening here with this one, because I think it'll help to clear up any confusion about what's happening with this form. I'm going to look at this graph. I'm going to zoom standard. Okay, so clearly for this first function, that was the one that I graphed, we had a domain issue at 1, because if x is 1, the function does not exist because we end up getting 0 in the denominator. Okay, now you can see why, because we have this vertical asymptote occurring at x equals 1. But what's happening here now is that you don't actually know what's happening to the value of the function as you approach 1 from the left and from the right. Clearly, you're approaching from two different values. So this is not just a DNE, because you have a DNE minus another DNE. If you were actually to look at the other function, 2 divided by 1 minus x squared, graph that. Again, clearly you're going to have a domain issue at 1, and you have something similar occurring. On one side, as you approach 1 from the left, your function continues to go up towards infinity, kind of giving you a lead in here to next week. And then as you approach 1 from the right, the values of y are heading down to negative infinity. So this one is all over the place. You don't know what's happening. You don't know if it's infinity, negative infinity. But anytime you have some sort of an infinite value minus another, that's indeterminate. So this is a no-go. It's an indeterminate form. You might be wondering, well, like, what if I just had this? Like, what if it was just the first function without the second function in it? If it was just the first function, you could say does not exist. But because you're subtracting them from each other, you get an indeterminate form. So you're going to have to rewrite this function, and you're going to see now that we will actually get a value for this limit to pop out. But we're going to have to do a little bit of work on the function first. So take it out of the limit for a few minutes, because you're not going to want to keep writing your limit over and over and over again. Now, if I were you, I would rewrite this, because this is also a difference of two squares. And we're going to need to combine these into one fraction so I can get rid of this situation where I'm subtracting off these two DNEs. So I'm going to rewrite this as 1 plus x times 1 minus x in the denominator. Are there questions here? Now, if I want to write this as one fraction, you guys spend a lot of time doing this in your 098 class. One semester I taught 098, and I taught a Calc 1 class right after it. And this was when we were in person. But I realized that every single thing my Calc 1 students struggled with was something I taught in 098. It was just such a valuable class. And I actually would tell my Calc 1 students, and I didn't mean this in a condescending way, but I'm like, you guys, if you want, you can come sit in on my Math 98 class and just kind of refresh some of this algebra stuff. And some of them took me up on it once or twice, because this is a skill that you learn in Math 98. If you want to combine these into one fraction, you need to have a common denominator. If you want to get a common denominator, remember you're using each factor you see the greatest number of times it appears in any one denominator. You need to create an equivalent fraction. Your LCD in this case is going to be this denominator in your second term. We can recreate this by making your first denominator match the second one. If I do that, though, I need to multiply in the numerator by the same quantity that I multiplied by in the denominator. So remember, when you're creating equivalent fractions, technically you could just cancel out that quantity again and you'd get back what you started with, but you wouldn't want to do that because then you're undoing the work that you've already done. You'll have 1 plus x minus 2 divided by 1 plus x times 1 minus x. The order does not matter. And then you can rewrite this function as x minus 1. Actually, I'm going to need to do this more than one step, so I'm going to come over here. X minus 1 divided by 1 plus x times 1 minus x. And if you think you're done, be careful, because if you mentally try to find this limit again, if you're approaching 1, you're going to get 1 minus 1 in the numerator, which is 0. And then 1 minus 1 in the denominator will also give you 0. So you're still going to have an indeterminate form. Clearly, you need to work on this more. Whatever you do, don't cancel out the 1 minus x and the x minus 1. Those are not the same quantities. 1 minus x, x minus 1, you can't just subtract in any order you'd like. But what you can do is you can rewrite the numerator so that it does match this factor in the denominator so that you can cancel it. And the way you're going to do that is by factoring out a -1. Remember, when you factor out a quantity, you're dividing by it. So if I divide each term by -1, well, now I can switch the order of my subtraction and write it as 1 minus x. Remember, you can always redistribute and verify that you did not actually change anything. You would get -1 and a positive x, which is exactly what you had. Don't multiply it back in, though, because the whole point was that you wanted to cancel out these common factors. And you end up rewriting this expression as -1 over 1 plus x. Now, there's no way that that could give you an indeterminate form. It's one fraction, and it's got a constant in the numerator. So sometimes there's a little bit of work that you have to do inside the function before you can apply the limit. Now, before we actually work on the limit again, does anyone have a question about how we rewrote the function using algebra? I'm waiting for, oh, Renee. Yes, what's your question?
So when you were doing the 1 plus x minus 2 over the 1 plus x and times 1 minus x, why didn't you just add the 1 to the negative 2 to get x minus 1? Oh, it looks like you did. But then where'd the negative come from on the numerator?
Here?
Yeah.
Oh, well, I just wanted these two to match, but the order of subtraction was opposite.
Oh, okay.
I factored out the negative one.
Okay.
Yeah, so that's a technique that you can always use if the order of subtraction is opposite than the way you want it.
Mm-hmm.
Does that answer your question?
Yeah.
Okay, wonderful. I'm glad you asked. Any other questions on the algebra? Okay. All right, so now we can rewrite our limit, and we're going to take the limit now of the equivalent expression. So we turned this fraction, or this difference of terms, into the fraction -1 over 1 plus x. And now we can go ahead and find the limit with direct substitution, and we'll get -1/2. So that one probably would have been a little bit easier to do in your table, just because there was less work to do in that case. I know tables always seem so grueling, but I think in this case you would have arrived at that conclusion a little bit faster. Okay, now the next type I'm going to show you is very important. They're all important, I know, but this is one that you will see in every calc textbook. You will very likely see something like this on your test, maybe even on a quiz, because it's important. So I'm going to do two like this. Okay. Notice that if you try to use direct substitution, you'll get the square root of 16 minus 4 divided by 10 minus 10, and you'll get 0 over 0. It's indeterminate. And this is another one that you probably saw on your 1-1 homework, this type of problem where you were looking at tables. Well, this one we're going to have to do using algebra, and we're going to have to rewrite this expression. But you might be wondering how we're possibly going to do that, because it's already written as one fraction, and there's nothing that you can really cancel out at this point. You can't really factor anything. So I'm going to show you what we're going to do. We're going to apply this technique all the time. We're going to rewrite the expression so we can work on it. So take it out of the limit for a minute. And what we're going to do is we're going to multiply the numerator and denominator by the conjugate of whichever piece of this fraction has the radical. So you're going to pick the piece with the radical, which is the numerator, and we're going to multiply the numerator and denominator by the conjugate of, in this case, the numerator. Now, if you don't remember what the conjugate is, it's something that you learned in Math 98, like everything else. If you never took Math 98, you took algebra in high school, and I know that was so many years ago. The conjugate is, remember when you did A plus BI times A minus BI because you were trying to undo the constant term on your imaginary numbers? You did that. You know what? Maybe you did that in college algebra, also known as Algebra 2. You took 112 at ECC. All right, so the conjugate means that you're going to switch the sign between the terms, not the sign under the radical. That one stays the same. But you are going to switch the sign in between the radical term and the constant term. And what you multiply by in the numerator, you must also multiply by in the denominator, otherwise you're changing the expression. But this quantity divided by itself just simplifies to 1, so you don't have to worry about anything there. Now, the whole point of doing this is that we're going to be able to get rid of some sort of troublesome terms here that are giving us the indeterminate form. So we're going to be careful that we FOIL the piece that includes the conjugate, and we're going to keep factored the part that does not include the conjugate. So the numerator is where we got the conjugate. That's where we're going to FOIL. If you feel like you can see this more easily with parentheses around it, that's fine. Do that. When I FOIL these, I'm doing first, outside, inside, last. So when I multiply the first terms, I'm multiplying the square root of x plus 6 times the square root of x plus 6. The square root of a quantity multiplied by itself just gives you the radicand back. Now, the whole point of the conjugate is that the outside and inside terms cancel. They become additive inverses. So you're going to have 4 times the square root of x plus 6, and then plus -4 times the square root of x plus 6. Those two terms will cancel. You don't even have to write them. The last terms just give you -16. Just because this is the first one I'm doing, I'm going to write out the plus 4 root x plus 6 minus 4 root x plus 6. You don't have to do that. I just don't want anyone to be confused and wonder what the heck just happened. Okay, so these are your first, outside, inside, last. In the denominator, leave it factored. Do not FOIL the denominator. Do not FOIL the piece that is where your conjugate did not come from. Leave it factored. If you end up FOILing it, you're going to realize that you don't know what to do because you're stuck. Don't do that. Okay, so the I and the O are additive inverses. They're gone. Simplify what's left in the numerator. You have x plus 6 minus 16. That's really x minus 10. And now you can see why you left the denominator factored. Because now you have factors of x minus 10 in the numerator and denominator that are going to cancel. Questions so far? Okay, so cancel out those factors, and that leaves you with not 0, but 1 in the numerator. And then in the denominator, you have the square root of x plus 6 plus 4. Now, once you've simplified that expression, well, now you can see that you're no longer going to get an indeterminate form because you have a constant in the numerator. So go ahead and apply your limit one more time to your new expression. So we're taking the limit as x approaches 10 of 1 over the square root of x plus 6 plus 4. And you're going to use direct substitution with the 10. I know it's not a polynomial, but you don't have to keep breaking these down. 1 over the square root of 16 plus 4. And you will get 1/8. I'm going to do another one similar to this. I'll go through it a little bit faster, but I generally find that it benefits students to see another one of these. And if I ask, they say yes. So this one will be D. This is the limit as x approaches 1 of x minus 1 divided by the square root of x plus 3 minus 2. And this is going to be very similar. If we go ahead and use direct substitution, you will end up with 0 over 0. One. Got 0 on the brain here. So go ahead and take your expression out of the limit. Multiply by the conjugate of whichever piece of your fraction is containing the troublesome radical, which in this case is the denominator. So I'm going to multiply by, and remember, don't change the sign under the radical, only switch the sign that's between the terms. And multiply it by the conjugate over itself. We want those outside and inside terms in the denominator to cancel. And then again, be careful because I want you to remember to leave the numerator factored because we're going to end up probably getting a factor of x minus 1 that's going to cancel. So leave your numerator factored. In the denominator, the square root of x plus 3 times itself is x plus 3. Don't even worry about writing the outside and inside terms because it's a conjugate. By definition of the conjugate, they're additive inverses. They're going to zero out. Your last terms will give you a minus 4. And then you can continue to simplify. And now you can see that that x minus 1 in the numerator is going to cancel with the x minus 1 in the denominator. That's why you left it factored. And from there, you can now rewrite your expression and try the limit again. And clearly this time you're not going to get an indeterminate form. So this will be the square root of 4 plus 2, which will give you 4. Okay, there's one last thing I want to do today. It has to do with the difference quotient, which you're going to see in chapter 2, and your book asks you a few questions about finding that limit. So I want to go over that, and then that will be it. Does anyone have a question on D before I do the difference quotient? All right, I'm going to define the difference quotient for you. What's happening here? You probably saw this in algebra. We usually show this first in algebra 2 just to sort of familiarize students with it because it is something that is used so often in calculus. For our intents and purposes, we're taking the limit as h approaches 0 of f of x plus h minus f of x over h. So when you saw the difference quotient in algebra, it didn't have a limit on it, but you were asked to evaluate f of x plus h minus f of x over h. Sometimes you see this with a delta x instead of an h. So I want to give you an example using this. Find the limit of the difference quotient for f of x equals 2x squared plus x. Now I'm giving you a function f of x. What we need to find is the function f of x plus h. Then we'll subtract off the f of x that I gave you and then divide it by h. So we need to simplify this so that we can find this limit. So first find f of x plus h. Like I said, you should have done this at some point before. If you didn't, no big deal. We've done a lot of evaluating functions. I'm pretty sure that your algebra review had something like this on it. Maybe not the exact difference quotient, but I think you were asked to find things like f of x plus h and maybe a question or two. I'm pretty sure, but there's a lot in there. So, okay. So we're going to do this. I'm going to take my function, and everywhere I see x, I'm going to substitute it with x plus h. So instead of writing x squared, I'm going to write x plus h, quantity squared. And then instead of saying plus x, I'm going to say plus x plus h. You don't have to have parentheses around this one. You do have to have parentheses around the squared terms. And don't forget that you're substituting x plus h everywhere you see x, in every single place. So we saw x in 2 places, we substituted in 2 places. And then we're going to simplify that because we're going to have to subtract off f of x. So to simplify, I'm going to square x plus h by multiplying it by itself. Remember that x plus h quantity squared does not equal x squared plus h squared. Very common algebra mistake. Don't do it. You cannot just distribute the exponents to each term. You have to actually FOIL it out. So I'm going to keep the 2 on the outside, and I'm going to FOIL the binomials first. So I'm going to do the first terms outside, inside, last. So x times x is x squared. Well, then what you get for the outside and the inside terms is x times h plus h times x. H times x and x times h are the same thing. So if I have xh and hx, I just have 2 of them. Pick the order in which you want to write variables. I like to just do them in alphabetical order, but it's up to you. And then add in your plus x plus h. All right, questions so far? So we will be doing quite a bit of this, by the way, in chapter 2. So get used to it. All right, we're going to simplify this further by distributing the 2 into the parentheses, and then in the next step, we'll combine like terms. So you'll have 2x squared plus 4hx plus 2h squared plus x plus h. And actually, we don't even have any like terms to combine. So we're actually done right now with f of x plus h. Oh, and by the way, notice that if you would have incorrectly FOILed this by distributing the exponents, you would have lost the 2hx. So just be careful. All right, so now we're going to start putting this difference quotient together. I'm looking for f of x plus h minus f of x divided by h. So we'll do this second. So I'm going to take my f of x plus h, which I just found. 2x squared plus 4hx plus 2h squared plus x plus h. And I'm going to take off f of x. Now be very careful when you do this because you're subtracting off more than one term. That means you're going to have to distribute that negative sign. Or if you want, you can just switch the sign on the successive terms. If I were you, I would just write it twice. You know, we hate having to write things more than we absolutely have to. But it's really good for you. And as your math teacher, I'm here to tell you what's really good for you mathematically. All right, so we're going to have to distribute. Yoink. So this was our f of x plus h. And we're subtracting off f of x. So f of x plus h minus f of x divided by h. Okay, so when we subtract this off, we'll have 2x squared plus 4hx plus 2h squared plus x plus h minus 2x squared minus x. And then we'll simplify. Now, if you've done this correctly, both of your f of x terms that you put in here are going to become additive inverses and they're going to cancel. What I mean by that is you have 2x squared and negative 2x squared. And you also have negative x plus x. As long as you've done this correctly, you're going to see that that happens in every case. So if you still have terms left here at the end, you should be like, wait a second, something is awry. And you'll look again. All right, that leaves you with 4hx plus 2h squared plus h divided by h. Now, I know how you guys are. Some of you are just going to say, okay, fine, I have an h in every single term. I'm just going to cancel out I'm going to cancel out an h in each term. That's fine. As long as the h is in every single term, you can cancel it out one factor of each one. I just want to make sure that we understand that when we're doing that, you have to be able to actually factor it out, which you can as long as it's in every term. But if you want to see why that works, factor out the h. And that leaves you with 4x plus 2h plus 1. Remember, when we take h and divide it by h, we still get 1 divided by h. And now you can see that, okay, fine, we factored it out. Let's cancel it out. And like I said, you don't have to show that as long, I mean, if you can just get rid of 1 in each term, that's fine. But I always have a student who asks me, how come you can do that? Which is why I've gotten into the habit of showing this. All right, now all we're doing is finding the limit as h approaches 0 of the difference quotient. So this is your difference quotient. And we're going to find the limit as h approaches 0 of 4x plus 2h plus 1. Now, when h goes to 0, x is not going to 0, only h. I think that's something that students miss here. We're so used to thinking about the variable x. We're not touching x in this case. X is being considered similar to a constant. It's going to stay. It's the h that's going to cancel. So, or I'm sorry, the h is going to go to 0. I shouldn't say cancel. But the 4x and the 1 will remain. If you are wondering where that came from, we had 4x plus twice 0 plus 1. And it's okay that your answer has an x in it. It should. It's supposed to. Okay, that is all I have to say about 1.2. So for your asynchronous work, I'm going to talk about continuity, which is 1.3. And then actually this is exactly what I was planning. So I should have recorded it earlier, but I was like, you know, I'm probably not going to get exactly where I want, so I'm just going to wait my plan was do 1.3, cover squeeze theorem from 1.4. That's what I should have done. That's what I'm going to do for your asynchronous work. I'm going to cover continuity in 1.3, and I'm going to cover the squeeze theorem from 1.4 and introduce some special trig limits. I don't want to start working on too many of the trig limits asynchronously, though, because it seems like students tend to have a lot of questions on them. So I do want to make sure that I don't do too much asynchronously. So, all right, so this is 1-2. I'm going to remember to put up homework right now because I forgot last night to put it up right away. Most of you got to it super quickly anyway. And then I'm going to record you an asynchronous lecture for 1-3, and then a little tiny bit of 1-4. And then we'll pick this up again on Monday with 1-4. Start a little bit 1-5. We'll finish 1-5 on Wednesday, and your test is technically scheduled for Thursday. So we might pop in a little bit of 2.1 into your lecture on Wednesday because it really goes with chapter 1. I usually include it on that first test. So I'll kind of see how we're doing next week and see how everyone's feeling. And then we'll start the derivative rules the week after, or asynchronously next weekend. That's sort of my plan. So I'm going to put up some homework for you guys. And then at some point later this evening, before 2 a.m., because that's the official time by which I like to be in bed, I will have some sort of recorded lecture for you that is going to have a YouTube link. I'll email it to you, but I'll also post it to D2L so you have access to it. Don't skip over it because you're going to be quizzed on Monday, and it's going to include anything I covered tonight and anything that you are being asked to do asynchronously over the weekend. I will also put up a homework assignment for your asynchronous work, and all of that stuff I assign tonight and that I assign asynchronously over the weekend will be due on Monday. Okay, if you have questions, stick around another minute or two. Otherwise, that's all I have for you. Have a wonderful evening.